Today's deep dive is into a stack of engineering blueprints that, honestly, it reads a lot more like a survival manual for a high-tech war zone.
Oh, yeah. It really does.
Yeah, we are looking at a massive, incredibly paranoid, functional safety document for hybrid and EV dual motor controllers.
Right.
Specifically, we're dissecting the protection strategies for what engineers call gate drive faults and undervoltage lockout, or UVLO and traction inverters. So our mission today is to really understand the microscopic, almost invisible chaos happening inside an electric vehicle and how engineers manage to keep it safely on the road.
It is a totally fascinating set of documents. I mean, when you look at the sheer density of the technical specifications here, we're talking about a five-dimensional defense strategy covering 45 core faults.
Wow.
Yeah, you realize that keeping a modern electric vehicle from turning into a high-speed hazard, it requires an entirely different level of engineering philosophy.
Right?
It's not just about making a motor spin. It's about anticipating how the fundamental laws of physics will actively try to destroy the system.
Actively destroy it.
Yeah.
And to set the stakes for everyone listening, if you have an EV parked in your driveway, or if you're commuting in a hybrid right now, this invisible battle is happening inches from your feet.
Literally inches.
Yeah. The traction inverter we're talking about is essentially the brain of the car's propulsion. It takes the heavy, direct current, the DC juice sitting in your battery pack,
Right.
and it violently chops it up into alternating current to make the motor spin. And it does this using incredibly high-speed switches.
Yeah.
We're talking about silicon carbide MOSFET.
Yeah. So the silicon carbide or silicon switches, those are the muscles.
Okay.
If the inverter is the brain, the gate drive is the nervous system.
I like that analogy.
Yeah, it's the specific electrical pathway that tells those switches exactly when to open and close, holding back or releasing a massive reservoir of energy.
Which brings us right to the core threat. I was looking through the ASIL D safety classifications in our sources. ASIL D being the highest automotive safety integrity level.
The absolute highest, yeah.
Yeah, meaning a failure here could be fatal. If this gate drive system misfires by literally a fraction of a millisecond, it triggers what the engineering world casually calls a shoot-through.
Shoot-through.
Right. But reading the physics of a shoot-through, it's basically a catastrophic short circuit.
Yeah.
The positive and negative sides of a massive high-voltage battery suddenly connect directly through the inverter.
It is absolute devastation for the hardware.
I can imagine.
If a shoot-through occurs at highway speeds, the motor can lock up instantly. Components vaporize from the heat, and the driver experiences a sudden, violent loss of vehicle control.
Oh, man.
The wheels could literally seize while you're doing 70 miles an hour.
Which perfectly explains the obsessive paranoia in this document.
Exactly.
Achieving that ASIL D rating isn't something you can just patch with a software update. Software crashes.
Right. Code gets stuck in loops.
Exactly. Code gets stuck. So the defense strategy they outline relies on redundant hardware, molecular-level physical design, and a deep understanding of how the system degrades over time. Before we get into those defenses, though, I want to unpack the 4 ways this document says the drive tries to inadvertently kill itself.
Let's do it.
Starting with the power supply.
Yeah, so this is a classic vulnerability. To control a massive, high-voltage traction battery, the gate drive relies on a localized, low-voltage power supply, usually drawing from the standard 12-volt system in the car.
Right, just the normal battery.
But that 12-volt supply is not perfectly stable.
Not at all. I mean, think about driving in freezing temperatures.
Yeah.
You've got the seat heaters on, the cabin heater is blasting, the steering wheel is drawing power, and then you slam your foot on the accelerator to merge onto a highway.
Right, a massive sudden draw.
The document specifies that under these heavy, complex loads, the low-voltage supply can suddenly sag. It can plunge from 12 volts down to 6 volts for maybe 20 milliseconds.
And 20 milliseconds is the blink of an eye to a human. But to a microprocessor operating in the megahertz range, it is an absolute eternity. If the internal capacitors on the circuit board don't have enough reserved energy, what engineers call hold-up time, the voltage feeding the gate drive slips below a critical threshold.
The undervoltage lockout threshold.
Yes.
The UVLO. I saw that listed at roughly 13.5 volts. My initial thought was, okay, if it drops below 13.5 volts, the switch just turns off, right?
It's
just like a flashlight dying. But it's much worse than that.
It is significantly worse. Because a silicon carbide switch isn't a simple mechanical light switch.
Right.
It requires a strong, definitive voltage to fully saturate, to basically open the floodgates completely.
Okay.
If the voltage sags below that 13.5 volt line, the switch enters this terrifying, high-impedance middle ground.
Uh-oh.
It's not fully closed, and it's not fully open.
So it's trying to pass hundreds of amps of current, but it's physically resisting the flow at the same time.
Precisely. And when you force massive current through high resistance, you generate instantaneous localized heat.
Right.
The silicon die inside the switch literally begins to bake itself from the inside out within milliseconds.
I was trying to visualize this, and the closest I got was imagining you're scuba diving at 100 feet and someone momentarily pinches your air hose.
Well, that's a good one.
You don't immediately drown in that very first second, but the pressure drops, your muscles freeze up, panic sets in, and the entire biological system just collapses.
Mechanically, the system is suffocating for voltage, and the thermal runaway that follows is irreversible.
Wow.
But as dangerous as that is, it's a known quantity. Engineers have dealt with voltage sag for decades.
Right.
The next vulnerability we should look at is much more insidious because it's a byproduct of the EV industry's own progress.
Yeah, I wanted to get into this.
It has to do with how incredibly fast these new silicon carbide switches operate.
The switching speeds blew my mind. The source notes these chips are changing voltages at a rate of 10 kilovolts per microsecond.
Yeah, it's staggering.
And in the most extreme edge cases, they are swinging up to 50 volts per nanosecond. To put that in perspective, light only travels about 1 foot in a nanosecond. In the time it takes light to move from your steering wheel to the dashboard, the switch has slammed 50 volts of potential across the circuit.
The efficiency gains from switching that fast are incredible. It's why modern EVs have the range they do. They aren't wasting energy in the transition between on and off.
Because it happens so fast.
Exactly. But that violent speed introduces a massive physics problem. In basic electronics, ground is supposed to be your absolute bedrock, your 0-volt reference point.
Right, the baseline.
Everything in the logic circuit measures itself against that zero.
But when you slam 50 volts per nanosecond into the system, you get something called displacement current, right?
You do.
I was reading up on the formula for this, and it essentially says that an incredibly fast change in voltage will force a current across an insulator, even if there's no physical wire connecting the two sides.
Right.
It injects high-frequency common mode noise across the isolation barriers.
That's what we call the sledgehammer effect. Hitting the circuit with that kind of speed is like striking a massive bell.
Oh, wow.
It injects parasitic capacitance directly into the logic ground. If this noise exceeds the microchip's common mode transient immunity, or the CMTI, you experience a phenomenon known as ground bounce.
Which means the bedrock of the entire circuit is literally shifting. The 0-volt reference point spikes.
And when the ground shifts, the sensors are completely blinded.
Man.
A microchip might suddenly read a totally normal, safe signal as a catastrophic fault. Or worse, it might ignore a real fault because its baseline is bouncing around.
So it's basically hallucinating.
Yes, it shuts down the car for a ghost reading. The irony here is profound. The very mechanism that makes the car so efficient, the lightning-fast switching, is creating localized electrical earthquakes that confuse the safety sensors.
It's like building a race car so incredibly fast that it literally outruns its own headlights.
Exactly.
Well, sensors can't see the road anymore, so we have voltage suffocation and electrical earthquakes. The third vulnerability feels almost cruel because it relies on the pure brute force physical reality of the car. It's the mechanical harmonics.
This is where electrical engineering collides violently with mechanical engineering.
Right. An electric motor naturally hums and vibrates. Depending on the speed, that vibration is usually sitting somewhere between 100 and 1,000 hertz. Combine that constant hum with the random chaotic kinetic energy of driving over potholes or cobblestone streets, and you get a chaotic wave of physical force moving through the chassis.
And the printed circuit board, the PCB that holds all these delicate microchips, has its own natural resonance frequency.
Like a tuning fork.
Think of a singer hitting the exact pitch to shatter a wine glass. If the motor's vibration combined with road noise hits the PCB's resonance frequency, the board doesn't just sit there. It begins to warp and flex on a microscopic level.
The document says this flexing causes micro disconnects and soldered joint fatigue. Now, I really got to sit with this for a minute.
It's a crazy concept.
Yeah. We're talking about a digital control signal, the code telling the motor to spin. And you're telling me the literal hum of the motor can shake a microscopic solder joint until it cracks, physically severing the line of communication.
It absolutely can. We have to remember that a digital signal, the ones and zeros of software code, is ultimately just a physical voltage applied over a piece of conductive metal.
Right, it's actual electrons moving.
Over millions of cycles, the physical displacement from that resonance frequency causes what we call fretting wear.
Fretting wear.
Yeah. The tiny droplet of solder holding a crucial gate resistor to the board slowly develops a microscopic fault line.
Wow.
Eventually, for just a fraction of a microsecond, the physical connection separates.
The wire snaps.
The wire snaps, and when it snaps, the voltage drops to zero. A critical command is lost in the void, all because the acoustic and physical vibration of the vehicle dismantled the hardware on a molecular level.
That is wild. The mechanical reality of driving kills the digital signal.
It's a harsh environment.
Okay, the last vulnerability ties back to those insanely fast switching speeds. The DESAT path interference.
DESAT stands for desaturation.
Yeah.
It's a vital safety circuit specifically designed to detect the shoot-through shorts we talked about at the beginning.
Okay.
It sits there, constantly monitoring the voltage across the switch to ensure it hasn't shorted out.
But because of that high DVDT, the extreme change in voltage over time from the silicon carbide chips, we see that displacement current pop up again.
Right.
The violent voltage swing forces a tiny rogue electrical charge across the gap and accidentally charges up the DESAT filter capacitor.
It's a phantom charge.
Yeah.
And the safety protocols are rigid. If that capacitor hits a 7-volt threshold, the system is programmed to panic. It believes there is a fatal short circuit happening right that second.
So it forcefully shuts down the propulsion, a completely false positive.
Yes.
The system strands you on the side of the highway because a ghost current hallucinated a fatal error.
Exactly. So those are the environmental and physical realities these engineers are up against. The system is constantly trying to suffocate, blind itself, shake itself to pieces, and hallucinate errors.
Which makes the defense mechanism so critical. The documentation pivots here into what it calls the technical architecture, or the system's reflexes.
Yep.
We've established how the physics of this environment actively works to destroy the control signals. The natural question is, how does a vehicle actually survive this? The timeline dictated by ASIL D is incredibly strict.
Extremely strict. The fault-tolerant time interval, the FTTI, dictates that the entire system must reach a completely safe state in under 60 milliseconds from the moment a fault occurs.
60 milliseconds.
But if you wait for software to recognize the fault, log it, decide what to do, and send a command, you're already too late.
The car's already gone.
The hardware itself has to react in under 2 microseconds.
2 microseconds.
Yeah.
I want to focus on that 2 microsecond hardware reflex. They use high-precision window comparators inside the isolation chips.
Yeah.
If they detect the voltage dropping below that 13.5-volt UVLO line, they don't send an alert to the main microcontroller. They don't run a diagnostic.
There is zero time for a software handshake. It is entirely autonomic, like a biological reflex.
Like flinching.
Yeah, if you touch a hot stove, your spinal cord pulls your hand back before your brain even registers the pain.
Right.
The chip violently shorts the gate to the ground in under 1 microsecond, forcing the switch to turn off before the silicon can enter that high-heat, half-open state.
And as it pulls the emergency brake, it flips a dedicated hardware pin, the NFLT pin, to let the main computer know it just took action.
Exactly.
Which cascades into the broader system defense they call FCCU gating. I found this piece of the architecture fascinating. You have 6 total switches running the 3 phases of the motor, and they all have these dedicated fault pins.
Right.
The engineers group them together using wired or all logic.
The wired OR architecture is brilliantly blunt. All those fault pins feed directly into the microcontroller's safety management unit. If any single one of those pins drops, indicating a fault, the logic gate triggers instantly.
Within 100 microseconds, it locks out all the pulse width modulation signals. It entirely cuts off the control signals to the motor. It bypasses the software entirely.
It acts with absolute prejudice. It doesn't analyze the individual pins to figure out which specific switch failed. Right. It just shuts the entire control path down.
I was trying to map this to a real-world scenario, and it's basically like a fire alarm in a massive apartment complex.
Okay, yeah.
If a smoke detector goes off, the automated system doesn't wait to check if the fire is in room 3B or 4A. It doesn't send an email to the building manager. It just immediately shuts off the main gas line to the entire building.
When you are dealing with catastrophic high voltage, you act first and you ask questions later.
But you do eventually have to ask the questions, which is where the software finally catches up to the hardware. While the analog circuits are slamming on the brakes, the software is running at 10,000 times a second. It uses an SPI daisy chain to interrogate the microchips.
SPI stands for Serial Peripheral Interface. The daisy chain means the chips are linked sequentially, passing the data down the line.
Got it.
The microcontroller sends a command to read the internal fault registers, specifically the 0xFF registers.
And here's where the precision comes back. The software reads the bits. If bit D6 or D7 is flipped, it knows definitively it was a UVLO power sag. If bit D1 is flipped, it knows it was a deficit charge loss. It can diagnose exactly what happened with over 99% accuracy.
This interrogation is a strict requirement for ASIL D compliance.
Yeah.
You can't just throw an error light on the dashboard.
Right.
You have to mathematically prove exactly why the hardware tripped. Without that data logging, you can't implement an adaptive recovery, and you can't prevent the driver from just restarting the car and driving straight into a second fatal failure.
And how it recovers, the adaptive fallback, is where this document gets into some truly counterintuitive physics.
Oh yeah, this part is wild.
How the system saves itself depends entirely on how fast the car is moving. If you're driving at low speeds, under 2,000 RPM, it triggers an active open circuit. It just stops sending power, opens the switches, and lets the motor freewheel to a halt. That makes perfect sense.
It does.
But at highway speeds, over 7,200 RPM, the document strictly bans freewheeling. It absolutely forbids it.
Because at 7,200 RPM, the physics of the electric motor flip on their head.
Right. At high speeds, if you just let the motor freewheel, the spinning magnetic field inside the motor induces a massive reverse voltage.
The back EMF, or back electromotive force.
Right.
The kinetic energy of the car is now spinning the motor, and that motor is acting as an incredibly powerful generator. At highway speeds, the magnitude of that back EMF is like a tidal wave of voltage rushing backward through the heavy orange cables straight at the inverter. If you leave the switches open and just let it freewheel, that reverse voltage will easily exceed the dielectric limits of the components. The capacitors will blow, and the silicon will shatter.
So to prevent this, the software executes a stepwise active short circuit.
Yeah.
First, it intentionally shorts two phases together to suppress demagnetization. Then, 1.5 milliseconds later, it shorts all three phases of the motor together. I really struggled with this when I first read it. To save a high-voltage system from a catastrophic failure at 70 miles per hour, the computer intentionally short-circuits the entire motor.
I know, it sounds like absolute madness.
It does.
You're intentionally doing the one thing you're usually trying to prevent. But you have to think about what happens to magnetic energy when you short those coils.
You're creating a closed loop.
Exactly. By shorting the three phases together, you trap that massive generated current entirely within the motor windings. You cage the energy.
Okay, I see.
The current circulates inside the motor, creating a massive counter torque that safely breaks the physical rotation. But more importantly, it crushes the voltage spike. The documentation notes that this active short circuit clamps the bus voltage to a safe limit, keeping it firmly under 720 volts.
It's an electrical judo move.
That's a great way to put it.
It uses the beast's own kinetic energy and physics against itself to pin the voltage down. It is a brilliant reflex. But obviously, surviving an attack is great, but avoiding the attack altogether is the actual goal.
Sure.
And that transitions us perfectly from the reflexes into the design prevention, the DFMEA phase. How do you design the physical circuit board so these chaotic faults never trigger in the first place?
The first line of defense goes back to that 12-volt power supply sag. You can't stop the 12-volt battery from dropping when the driver turns on the heater and floors the accelerator.
You can't control the driver.
But you can buy yourself time.
They use specialized low ESR capacitors, equivalent series resistance. These capacitors are basically high-efficiency, localized energy reserves designed to guarantee 20 milliseconds of backup power.
Right.
But they pair that physical hardware with a really clever software trick. Dynamic frequency scaling.
Right. The system is constantly monitoring its incoming voltage line. The microsecond it detects the voltage beginning to sag, it doesn't just wait to die.
Yeah.
It actively lowers its own switching frequency.
I was thinking about this like a marathon runner. If you realize you're running out of oxygen at high altitude, you don't keep sprinting.
No, you pace yourself.
You deliberately slow your breathing and your pace so your body consumes less oxygen.
It's the exact same principle. By switching slower, the gate drive consumes significantly less power from those backup capacitors.
That makes sense.
It stretches that reserve juice, essentially holding its breath just long enough for the 12-volt battery to recover and stabilize.
Okay, so that handles the voltage sag. Next, they have to address the electrical earthquakes, the ground bounce caused by the displacement current.
Ah, yes.
They mandate chips with incredibly high CMTI ratings, over 100 kilovolts per microsecond. But they also implement something called an active Miller clamp. I fell down a rabbit hole reading about the Miller effect in MOSFETs.
It's a deep rabbit hole.
It is. It's a parasitic capacitance within the transistor itself that can cause it to accidentally turn on when it gets hit by those incredibly fast voltage spikes.
The Miller capacitance is an inherent flaw in the physical structure of the silicon. When that 50 volt per nanosecond spike hits the drain of the MOSFET, the internal capacitance couples that spike directly to the gate.
Oh, wow.
It literally injects a phantom turn-on signal into its own control mechanism.
So the active Miller clamp is the solution. It's an additional low-impedance switch built directly into the drive pathway. If the gate voltage drops below 2 volts, which means the switch is commanded to be definitively O-off-F, the clamp activates. It forcefully ties the gate directly to the logic ground.
It's not just passively turning the switch off, it is actively throwing a heavy physical deadbolt across the door.
Right.
Even if a massive spike of common mode noise rips through the circuit and tries to nudge the switch open via that Miller capacitance, the clamp holds it firmly at 0 volts. The noise is safely shunted to ground.
It bolts the door to the floor. I love that. Now, speaking of the physical environment, we have to talk about the vibration and those micro disconnects.
This is such a cool engineering solution.
The designers mandate a very specific component list to deal with this, specifically Class 1 C0G ceramic capacitors.
Also known as NP0 capacitors. This is a beautiful example of material science solving a chaotic electrical problem.
Right, because standard multi-layer ceramic capacitors, the cheap ones used in most consumer electronics, are often made with barium titanate.
Yes.
And barium titanate has a strong piezoelectric effect.
Just like the clicker on a gas grill.
Oh, perfect example.
You apply physical-mechanical stress to the crystal,
Yeah.
and it generates an electrical spark.
Exactly.
Yeah.
So if you put a standard capacitor on a circuit board that's bolted to a vibrating traction motor, the literal physical shaking of the car squeezes the capacitor, and it generates its own rogue electrical voltage.
It makes its own noise.
The vibration turns into electrical noise. The board acts like a microphone picking up the acoustic energy of the engine.
The microphonic effect. It would constantly inject false signals into the ASIL D safety monitors.
Right.
But the Class 1 COG capacitors use a completely different dielectric material, usually a calcium zirconate blend.
And calcium zirconate has 0 piezoelectric effect.
None.
You can hit it with a hammer, you can shake it at 1,000 hertz, and it will not generate a single millivolt of noise. They essentially change the chemical makeup of a tiny component to defeat a massive mechanical vibration problem.
And they don't stop at the component level. They attack the mechanical harmonics at the macro scale of the entire circuit board through dynamic frequency avoidance.
The 3D finite element analysis. The engineers build a complete virtual model of the circuit board.
Right.
They simulate the exact 100 to 1,000 hertz vibration range of the motor, and then they physically redesign the board's shape, move the heavy components around, and change the mounting points so that the board's natural resonant frequency completely misses that danger zone.
They map out the acoustic standing waves in virtual space.
Yeah.
And to ensure the physical board matches the simulation, they use rigid metal bars and heavy epoxy potting.
Wow.
They lock the physical geometry down so tightly that the maximum allowable flexing of the board under extreme vibration is less than 10 micrometers.
10 micrometers. That is roughly a tenth of the thickness of a human hair. By restricting the flex to that microscopic level, they completely eradicate the mechanical stress that causes the solder joint fatigue in the first place.
Yes.
The wire never snaps because the board never bends.
It's a perfect theoretical blueprint. But as any engineer knows, a flawless design on a computer screen means absolutely nothing if the factory floor can't build it perfectly every single time.
Which brings us to the manufacturing reality, the process controls, or the PFMEA. How do you prevent a tired factory worker or a slightly miscalibrated machine from ruining this masterpiece?
You rely on automation and microscopic non-destructive inspection. The tolerances are too small for human eyes.
The document outlines a process called automated X-ray inspection, or AXI. Every single finished board runs through a 3D X-ray machine, specifically to look at the internal structure of the microscopic solder joints hiding underneath the massive microchips.
Right.
They're looking for voiding.
When solder paste is heated in the reflow oven, it melts, off-gases, and solidifies. During that process, microscopic bubbles of trapped air can form inside the joint. These are voids.
And the physical rules enforced here are incredibly strict. The total voiding rate across the entire component must be under 5%, and no single contact pad can have more than 1% voiding.
Very strict.
I was reading about why voiding is so dangerous, and it comes down to current crowding. If there's an air bubble in the solder, the massive electrical current has to route around the bubble, creating a concentrated micro hotspot of thermal energy.
And thermal energy causes expansion. You have copper expanding at a different rate than the fiberglass circuit board, and that localized thermal stress concentrates directly on the void.
Oh, so it tears itself apart.
That is exactly where the microscopic crack will originate. By enforcing that 1% limit, the factory software is enforcing the material physics the designers calculated.
And if a board fails that X-ray scan, it doesn't just flash a red light for a human to check. The factory's manufacturing execution system, the MES, physically locks the conveyor belt.
That's right.
The bad part is trapped. It literally cannot move forward in the assembly line.
An automated hard stop. The system does not allow human error or complacency to override a structural defect.
Now, my absolute favorite process control on the floor deals with the physical connectors, the plugs going into the board.
Oh, the grease.
The grease. To stop fretting corrosion from the micro vibrations, robots inject a highly specialized conductive fluorosilicone grease into the connector pins. Niagel 760G is heavily referenced.
Right.
It coats the metal and stops oxygen and moisture from getting into the microscopic scratches caused by vibration.
But the critical factor is the volume. They must inject an incredibly precise layer, exactly 10 micrometers thick.
10 micrometers again.
Too much. And it creates a mess that attracts conductive dust. Too little, and it fails to protect the metal.
And you can't see 10 micrometers of clear grease with a camera, so they mix the grease with a UV fluorescent tracer fluid.
Like James Bond stuff.
Yeah, exactly. A high-resolution camera hits the connector with ultraviolet light, and the machine mathematically verifies 100% coverage based on the glowing footprint before it unlocks the station.
It's brilliant. If a dispensing nozzle clogs and leaves a 2-microsecond gap in the grease, the UV camera catches it. Because if it didn't, if that car went out into the world 5 years down the line, after millions of microscopic vibrations on a bumpy highway, oxygen gets in.
Right.
Corrosion builds up on that single pin, the electrical resistance spikes, the UVLO signal drops, and the inverter shuts down at 70 miles per hour. That UV camera inspecting glowing grease is literally saving lives.
The final step on the floor is the digital handshake, the built-in self-test, or BS. Before any unit leaves the factory, a test bench interfaces with the chip and forces it to simulate its own faults.
Right.
It electronically verifies that the physical hardware thresholds, the 13.5 volts for the power sag, the 7 volts for the ghost short circuit, perfectly match the software's code base.
Exactly.
If there's even a 0.1 volt discrepancy, the unit is flagged and scrapped.
You verified the design, and you verified the assembly. But before you can put the ASIL D stamp on it and put it to mass production, you have to prove that everything we just talked about actually works in the brutal reality of the physical world.
Which brings us to the production validation phase, the trial by fire.
The fun part.
This is where they intentionally try to destroy their own creation. The testing protocols are terrifying. The first one is the shake and bake test.
Shake and bake.
They take the completed circuit board and bolt it to an industrial vibration table. They shake it violently across 3 different axes, sweeping from 10 hertz up to 2,000 hertz at massive G-forces.
Simulating the absolute worst-case scenario of a failing motor bearing combined with a severely damaged road surface.
And while they are shaking it, they put it inside a thermal shock chamber. They blast the board with temperatures rapidly swinging from negative 40 degrees Celsius, so deep winter freeze, up to positive 150 degrees Celsius, which is significantly hotter than boiling water.
Right.
And they run heavy electrical power through it while doing all of this for over 500 uninterrupted hours.
Consumer electronics like your laptop, your phone, they would turn into absolute dust in a fraction of that time.
Oh yeah, totally.
The thermal expansion and contraction alone would shear the chips right off the board.
But the traction inverter must survive, and the pass criteria is insane. After 500 hours of being shaken and boiled, the electrical contact resistance across the board cannot change by more than 1.2 million.
0.2.
1.2 thousandth of an ohm. Furthermore, the data loggers cannot detect a single electrical signal drop lasting longer than 1 single microsecond over the entire 3-week test.
This test validates the entire chain. If the design phase failed with the mechanical harmonics, or if the factory allowed a 3% void in the solder, the board will fail the shake and bake.
Right.
The crack will form, the signal will drop.
Next, they test the power reflexes with the power cut test. They put the system under heavy load and manually drop the 12-volt supply down to 6 volts for 20 milliseconds.
To test the hold-up time.
Exactly, just to prove those low ESR capacitors and the dynamic frequency scaling actually hold the line. Then, they forcefully drive the voltage below 13.5 volts to ensure the hardware violently pulls that emergency brake in under 2 microseconds. It has to act completely flawlessly every single time.
Which culminates in the final and undoubtedly the most dangerous validation test.
The 12,000 RPM dynamometer test, the ASIL D fault injection. They hook the entire motor and inverter system up to a massive test bench. They spin the physical motor up to its absolute maximum speed, 12,000 revolutions per minute under full mechanical load. The kinetic energy in the room is immense. And then the engineers purposefully trigger a catastrophic short circuit in the logic power supply.
They are intentionally trying to initiate a shoot-through while the motor is spinning at maximum velocity.
It's crazy.
If the safety systems fail, the physical destruction of the motor is guaranteed.
But to pass, the system has to recognize the fault, ignore the software, and execute that incredibly counterintuitive stepwise active short circuit.
Right.
Within 60 milliseconds, it must intentionally short all 3 phases of the motor together. It has to clamp that massive tidal wave of back EMF voltage securely under 720 volts, and it has to cap the short circuit current under 550 amps.
The precision is mind-blowing.
The system must trap the energy, cage the beast, and bring everything to a safe halt without a single spark. No fires, no melted silicon, and no demagnetized rare earth magnets.
It is the ultimate proof of concept, validating that human engineering can anticipate and corral the raw, chaotic forces of electromagnetism and kinetic energy.
When you step back and look at the sheer scale of this document, it changes how you look at the car in your driveway. We explored the bizarre, invisible physics trying to tear the system apart, the ground bounces injecting localized electrical earthquakes, the mechanical resonance vibrating solid metal to the breaking point.
Yeah.
We unpacked the autonomic hardware pulling the emergency brakes in microseconds and the software piecing together the wreckage.
We walked through the material science of calcium zirconate capacitors, the paranoia of X-raying microscopic voids, the UV glowing grease, and the sheer brutality of a 12,000 RPM fault injection.
It is a towering achievement of human ingenuity. But there is one tiny detail at the very end of this massive source document that I want to leave everyone with. It's a passing reference to the tools these engineers are developing next.
Okay.
It mentions that they are building a custom Python simulation tool designed specifically to model common mode transient immunity impedance.
The CMTI suppression model. This is where the automotive industry is rapidly pivoting.
Right.
We spent this entire deep dive talking about physical defenses. Epoxy potting, heavy metal bars, changing the chemistry of capacitors. But the future of complex engineering is moving beyond the physical realm.
We're talking about digital twins, right?
Exactly. With software-defined vehicles pushing speeds even higher, moving from silicon carbide to gallium nitride, which is even faster, engineers can't just build physical boards and see if they break.
It's too expensive, too dangerous.
Right. They're using Python and advanced physics engines to build complete, perfect virtual twins of these circuits. They are simulating how a 50-volt per nanosecond spike will ripple through the invisible parasitic capacitance of a circuit board before a single piece of copper is ever mined or etched.
They're fighting the electromagnetic war in the matrix before it ever reaches the physical world. It brings us right back to the beginning of our deep dive. The diagnostic landscape for modern vehicles has fundamentally changed.
It really has.
The comforting, simple idea of looking under the hood and seeing a broken belt or a snapped gear is gone forever. In its place, we have massive 3D simulations predicting microscopic electrical storms. It turns out keeping your family safely on the highway isn't just about the tread on your tires or the thickness of your brake pads anymore. It's about mastering the chaotic, invisible physics hiding in the nanoseconds.